We've already learned about Euler circuits, and now we're going to learn about something called Hamilton circuits. As you know, an Euler circuit is a circuit in a graph which uses each edge exactly once. A Hamilton circuit is a circuit that visits each vertex just once. So you've got to remember, for Euler circuit it has to do with edges. With Hamilton circuit it has to do with vertices. This concept, by the way, is named for the person whose photograph you're looking at there. That must be a rather early photograph in the history of photography. You can see it's from rather early in the 19th century. That's the mathematician William Rowan Hamilton. Now let's look at an example. Here I give you a graph with 6 vertices, and let's see if we can find a Hamilton circuit in this graph. Let's say we'll begin at vertex A. Now, if I want to specify a Hamilton circuit here, it suffices just to name the vertices that I want to visit in the order that I visit them, and that's because there are no multiple edges. So, for example, if I want to go from vertex A to vertex B, there's only one possible edge with which to do that. So I will first of all show you the vertex A. I'll list the vertex, and let's say I do indeed go to B, so I'm using that edge across the top. Now I can go downward on the right and go to vertex F, and from there the only thing I can do is go to vertex E, and now let me decide I go upward. I visit vertex C, and then I visit the only vertex that I haven't yet visited, which is D, and finally I take the edge, taking me back to A. So let me just draw that. I said we start at A, we go to B, we then go to F, then to E, then to C, then to D, and then back to A. That is our Hamilton circuit. Now, let me ask, please, that you pause this lecture video in just a moment and see if you can do the exercise that I've given you here. So I have shown you one possible Hamilton circuit in this graph beginning at vertex A. I'm asking you to find all the Hamilton circuits beginning at vertex A. So what you should do is take yourself a piece of paper and make a copy of the graph. Just draw that on the paper, and then somewhere nearby begin to list all the possible Hamilton circuits. Okay? Do that right now. Stop the video, and when you think you have an answer, then start it up again. Okay, now let me show you the possibilities. If you found 6 Hamilton circuits, that's correct. And maybe it's correct if you found 3. You may have made a clever observation that there were only really 3 to be found. But let me show you the 6, and then I'll explain why I say that 3 is also possibly a correct answer. So I've already shown you one possibility. Before I show you the other 5 possibilities, let me make an observation, and that has to do with the vertex F down at lower right. Notice that this is a vertex of degree 2. And since we're supposed to visit that vertex in our Hamilton circuit, that means we need to use both of those edges. That also means that if we're making our Hamilton circuit and we get to vertex B, then we have to go next to vertex F and then to vertex E so that we make sure that we visit vertex F. That's unless we've already been to vertex E already. So if we get to E before we get to B, then again we must go to vertex F and then to vertex B. So with that understood, let's begin to list all the Hamilton circuits. We'll start with the one I gave, which is A, B, F, E, C, D, A. Let's see if we can find another one that begins with an A and a B. And if it does, then of course, as we know, we have to go to F and then to E, and then the only other possibility, besides the one we already have, is to go to D, and then to C, and then finally back to vertex A, and that works. So there's another Hamilton circuit. Okay, so we've tried all the possibilities that begin with AB. Let's try AC. Now, from C, it seems that we could go either to B, or to E, or to D. Let's see what happens if we go to B. Well, we know if we go to B, then we must go to F, then we must go to E, and then the only one we haven't visited is D, and then we go back to A, and all of those edges are available, so that's another possibility. Let's also try AC followed by something else. Let's try ACD. Okay, now if we go ACD, then the only vertex that we haven't visited that we can get to is E. We know after E we must go to F, then we must go to B, and now back to A. So indeed, that's another possibility. Let's also see what happens if we try to do A followed by C followed by E. Well, in that case, we would have to go to F and then to B, but now there's no way to get to vertex D. So in fact, that didn't work. We can't go A, C, E. So now let's try going A, D to begin. After D, we could try going to C, and then we could try going to B. After that, we would have to go to F, and then to E, but wait a minute, that's no good. There's no edge from E to A, so we must have made a mistake when we went to B. So instead of going A, D, C, B, let's try A, D, C, E and see if that works. So we start A, D, C, E, then we know we must go to F, then we must go to B, and then we finish up at A. So indeed, that was another possibility. And now what haven't we tried? Well, after A, D, we haven't tried going to E, but we know after that we would have to do F, and then B, and then C, and then finally back to A. And now we've systematically exhausted all the possibilities, and here we are. We have 6 possible Hamilton circuits, as I said. Now, why did I say that 3 was also a correct answer? Well, that's because, as you may already have observed, if I, for example, take the first one that I've listed here, A, B, F, E, C, D, A, and read it backwards, that is to say, follow the Hamilton circuit in reverse, I get another one of the possibilities on my list. Here it is, A, D, C, E, F, B, A. So, you may or may not want to consider those as the same Hamilton circuit. Similarly, if I go A, B, F, E, D, C, A, which is the one that I'm now indicating, and read that one backwards, I get this one listed here, A, C, D, E, F, B, A, and finally the 2 remaining, which are still shown in black, are also a pair. One is the reverse of the other. Okay, so usually when we're looking for Hamilton circuits, we're going to say that a pair such as that is considered to be the same Hamilton circuit. But that's a convention that we need to agree upon. And here, just as a reminder, are the 6 answers that I found. Now, when we were looking at Euler circuits, we asked, how can we look at a graph and tell whether it has an Euler circuit? And we found a very nice answer. We learned a simple general criterion for determining whether a connected graph admits an Euler circuit. It went like this. Such a graph, a connected graph, has an Euler circuit if and only if all degrees are even. Now that's a very simple, easy to check criterion. It's called Euler's criterion. It would be nice then to say, well, what's the corresponding criterion for Hamilton circuits? In other words, if I give you a connected graph, How can you easily decide whether it has a Hamilton circuit? And the answer to that question, in fact, is nobody knows a nice, simple criterion for determining whether a connected graph has a Hamilton circuit. If you're given any particular graph, of course, just by some exhaustive method, you can figure out whether it has a Hamilton circuit. But nobody knows a nice, simple criterion analogous to Euler's criterion.